the circle with center O. Where, what does it say? Where P, sorry, my screen sharing thing is, P is not O. Okay. So that seems easy enough. So that's P, this is O, and A and B are 2 points on it. So I don't need to draw the segment really. So this is A and B. AP and BP meet. Oh, P is inside of it, so it's not on the circle. So I guess I'll just do the. Tell you what, I'll do this. We have P is inside it, and AP and BP meet it at C and D. So let me change P so that it doesn't look like it's on AO. Maybe something like that. This will be C and D. Probably would have been easier to draw. Yeah, this is a weird way to state the problem. AP, so S is the midpoint of PC. This is kind of random. Then we draw the circumcircle of ABS, and it intersects PD at T. And then the line through S perpendicular to AC intersects the circle at U and V. All right. And then we draw the perpendicular from T to BB. And it intersects at X and Y. Okay. So M and N are the midpoints of UV and XY. So those are basically the centers of those chords. M and N. And AM, so like OM and ON are perpendicular and parallel to those other two chords. And AM and BN intersect at Q. Interesting. And we want to show that P, Q, and O are collinear. That doesn't look right. So yeah, somewhere I
think you switched M and N.
Oh. UV. Yeah, you're right. This is M and this is N. And we have AM, BN. This looks like Pappus, kind of. Or either Pappus or Pascal, maybe. So yeah, it's weird how, so S is the midpoint of PC. Does that mean T is the midpoint of PD? Is it like?
Yeah, just by power of a point on P.
Okay. Oh yeah, because this is cyclic. That makes sense. Okay, interesting. All right, so we want to show P, Q, and O are collinear. I like this problem. So looks a little bit like Pappus, but not exactly. Is it the same as showing that A, T, N, M, S, and B lie on a conic or something? Well, not necessarily, because O is not defined that way. Like, I wonder if O and M and A, P, B are homothetic at Q. That looks like it could be. Well, A, B, and T, S are I'm a little confused. But I think that could be let's see if A, B, and NM are parallel. Yes. So yeah, it looks like these are probably homothetic at Q. I don't know if that's obvious.
And it also appears that the ratio is always 1 to 2. Like the ratio in which Q divides these segments.
Interesting. So AB is twice MN. Whoops. Let's see. So okay.
And I think with that we can just delete half the problem. I think we can just delete B and then show that that AM divides PO in like the ratio 1 to 2, and we can just ignore everything that has to do with B.
Okay, so we could just show AM cuts BO, PO in that ratio.
Yeah, and like none of that depends on B at all.
Okay. So AM divides PO. So P. Okay. It's like someone else just joined. So you're saying I could hide B and D, or hide B?
I mean, I'm saying you could even just like delete B and everything that depends on it, and it wouldn't really matter.
Delete B or P?
I mean, maybe, yeah, B.
Okay.
And like now all the clutter is gone, and we just need to show that it's the ratio is 1 to 2.
Okay. So UV. Then M is the midpoint. So these are parallel because they're both perpendicular. So it's the same as showing AP is twice OM. That's the same as showing P is the circumcent. Oh, so it's true because P is the orthocenter of AUV since PS equals SC. So basically the reflection of C over UV is P, so P is the orthocenter. And it's well known that the distance from A to the orthocenter is twice OM. So that basically proves it. So all these problems are too easy. I guess I could write it up, but yeah, that is too easy. So we'll have to look for harder problems. I thought this would be harder, Thailand team selection test. Because it wasn't that easy last time. So P is the orthocenter of AUV. Since the reflection of C, since it's the reflection of C over UV. All right. And AC is perpendicular to UV. So that means that AP equals 2OM. That's well known and also not very hard to prove. And that means that AQ, or that means that so we'll eventually show the homophily, right? Oh, Mohammed, did you just write something or say something? Anyways, okay, so AP is 2OM, and PQ is 2QO. And then similarly, we have BP is 2ON. And AP is parallel to OM and BP is parallel to ON, so they have to be homothetic. So that means that APB and NOM are homothetic. About Q with ratio -2 implies that PQ and O are collinear. Okay. All right, let's try to find some harder problems. Okay. Any questions on this proof from by anyone? All right. Let's see what else we can find. So why were they harder last time than this time? It was Thailand, TST. Let's see which problems I took. This one looks kind of interesting. Let's think about it. So medians intersect, but it's probably not hard. Yeah, so like this is what I did last time. This one looks not that easy. Also this one too. What do you think about this one? So we have 2 points on side BC. So I have one problem actually. So here's a problem I saw on a forum, and I haven't proven it yet. But this is from the Romantics of Geometry group. So it says you have a triangle ABC, and you draw the circles with diameters AB and AC. And then you draw the common tangent to these circles that lies outside of, let's see, you draw this common tangent. And then, trying to remember, sorry. So here's the common tangent. You end up wanting to show that some two triangles have the same incircle. So let me go look it up real quick on my phone. So, but yeah, I never solved this one, so we could do it right now. Scroll back a little bit. Yeah, lately in that group, they've been posting a lot of problems where you have to show that two triangles have the same size incircles. So that might have been a few days ago, but I'll find it. Just give me a couple moments. Scrolling. It's gotta come any second. Oh, there's another one that I didn't solve, that I just saw, but I'm gonna try to find this one. So I saw a problem like it. Oh, okay. Oh, here's a different problem. Sorry, sorry. Here it is. Okay, so you start out like this, and then you drop a perpendicular from A to FG, and you let it intersect this side at a point H, or I'll call it something different. Okay, let's say we want to show that ABK and ACK have the same in radius. All right. So yeah, the problem is to show that ABK and ACK have the same in radius. So these two circles obviously meet the foot of the altitude from A. So we could also draw these. And these points lie on the 9-point circle right here. All right. So I'll write up the description of the problem. So in triangle ABC, so say Romantics of Geometry Facebook group, in triangle ABC, the tangents let the common tangent to the circles with diameters AB and AC. That lies outside of triangle ABC. Meet those circles at F and G, respectively. G. The perpendicular, the altitude from A to FG. This is just for the people watching on the channel. A to FG meets BC at K. Prove that ABK and ACK have the same end radius. All right. There we go. All right. So this looks like a fun problem. AB and AC, sorry. Well, this common tangent also lies outside triangle ABC. So I don't know how, yeah, how do I describe this common tangent instead of this one? Maybe the problem's true with either of them. I don't think it is. So we really want the common tangent where both points lie on the same, where A, F, and G lie on the same side of BC. So I'll say touch with A, F, and G on the same side of BC. I think that should be okay. So if we draw the two incircles, let's do that. And then we could draw their centers. It's the same as saying that their centers are the same distance from BC. It's the same as saying MN is parallel to BC. I wonder, I think I have an idea. Yeah. So let's draw the feet of the angle bisectors from so we want to show MN is parallel to BC. That's the same as saying AM over AN. Whoops, I want this point to be point P. AM over AN is AP over AO. And we might be able to use the angle bisector theorem a couple times. So so AM over MP, I mean, it's the same as showing AM over MP is AN over NO. and AM over MP is AK over KP. So it's the same as saying that PK equals PO. Which is interesting. Yeah, we want to show PK equals PO. And we could use the angle bisector theorem again, probably, because we have AK over PK is AB over BP, and AK over KO is AC over CO. So we want to show that AB over BP is AC over CO. And AB over BP is actually AB over, I feel like I'm going in circles here, but I think I did something wrong. Oh, because I keep thinking P is this tangency point, which it's not. Yeah, so oh yeah, I can delete this. Well, is someone trying to draw? Sorry. Do you guys see that red line? Or, sorry, whoever's drawing the red line, please clear it. Is that Muhammad? I think you were drawing something before. Is that you? So undo the red line. I'm actually not sure how to delete it, to be honest. Sorry, can you delete that? Whoever just drew that red line. Otherwise, I'm not sure what to do. Sorry. Control F11. I'm gonna search how to, let's see, security. I'm not sure how to get rid of it. Mohammed, were you the one that drew this red line? Are you there? All right, I might clear. Okay, I think I see how to get rid of it. Here we go. All right. So yeah, I just have to click annotate and then it'll go away. All right. So can I show AB over BP equals AC over CO? Or that might be harder than just showing AK as median of APO. So let's see, so we're drawing a perpendicular. Okay, so FD is perpendicular to FG, and so is EG. So that's probably useful because we know DE is parallel. So if we want to show K as the midpoint of OP, and we know that AK is parallel to both of these, I wonder if we can use that to our advantage. I don't think these actually concur. No. It's an illusion. So yeah, how do we show the perpendicular from A? Isn't there some theorem about the A being the Dumpty point of some I forget what it is. Like, isn't like A the Dumpty point of FHG? I think that's like a well-known theorem, right? Or maybe it's the Humpty point, either the Humpty point or the Dumpty point. I'm not sure of triangle HFG. So see, I feel like we're really close here. It's the same as showing PK equals KO. I mean, it's the same as showing that. So yeah, we want to show AB over BP is AC over CO. And BP, I feel like I'm going in circles. Yeah. Let's see. PK, we want to show equals KO. Well, if that were true, we know angle MKN is a right angle. And so that would mean that like this point would be the circumcenter of MKN. Maybe that's the trick to solving this. So we want to show basically that like this point is the circumcenter of MKN. So is there anything else special about that circle? Not that I know of. I don't know if that really makes the problem easier or not. Is F, D, and P collinear? I don't think so, because I think I looked at it once. So they're not, but it almost looks like they concur on that circle, which is interesting. So it almost looks like FD and AM meet on the circle with diameter is that obvious? Maybe that's useful. Okay, I'm gonna delete this circle. I'm gonna delete a couple things. Delete.
It looks like AM is parallel to BF, which should be equivalent.
AM is parallel to what?
To BF.
To BF. Okay. Oh, interesting. So yeah, maybe that helps. So let's see. And then AN would be parallel to CG, if that were true. By the same. Okay, so I think that's probably. Let me just make sure, but I think that definitely looks true. And maybe that's just an angle chase. So if we knew they were parallel, then this would be an isosceles trapezoid, right? Or no, this would be a rectangle, I think, right? Yeah. And then we'd also have this would be a rectangle. But I'm missing something here. So what am I missing? So we're saying AO. Because this, yeah, we'd have to extend this AO. So we'd have like two rectangles kind of. Maybe they're similar rectangles, I don't know. So yeah, let's make this an acute triangle again, just so I don't get confused. So yeah, it is kind of interesting that F, D, and Q are collinear like that. So F, I mean, to get point F, we just need A, B, and C. Then we're saying FD meets this bisector. There's gotta, if we want to show that PK equals KO, I bet there's some congruent triangles that are somewhere. So one thing to note is AH passes through the midpoint of FG. Because AH is the radical axis of these two circles, and the radical axis passes through the midpoint of FG, because T has the same power with respect to both. Oh, you know what? I think that solves it, because, okay, T is the midpoint of FG, and I bet that ATG is similar to either AKO or AKP. Not sure, but okay. So angle TGA is equal to angle GCA, and if those are really parallel, that would be angle JAS, which would be angle KAO. So I bet I bet GAT is similar to AKO, and AFT is similar to AKP, and I bet using that similarity you can show that PK equals KO. But how do I show that similarity without assuming they're parallel? We're trying to prove that K is the midpoint of OP, but if I show those two similarities, I think that would solve the problem. So GAT and AKO, I want to show that those are similar. If the parallel is true, then one of the angles is the same. The other one, I think, is probably an angle chase. I want to show GAT is A-OK. So this is perpendicular to BC, this is perpendicular to FG. I wonder if let me just check it's true before I go too much further. So GAT 46.8 and AOK is the other one I wanted to show. AOK, yes. So GAT is 1/8. GAT is GCB. And we want to show that's AOK. Yeah, so if they're parallel, then these are similar. If GC is parallel to AN, then that would solve the problem. So we just have to show GC is parallel to AN. Okay. I mean, obviously GC, yeah, because we're just assuming all this stuff when we. So yeah, I mean, maybe point S makes it more confusing. Like I could delete that maybe. Because that's like equivalent. That's like what we want to show. So E is the center of the circle. I mean, we want to show AK, AN, AC, and AG are harmonic, right? So that might be a way to do it. So AK and I are, so that's the same as saying GI. We'd have to, yeah, that's the only thing. We'd have to see where these other two meet it. I don't know if that's that useful. You'd have to show that those are harmonic. I don't know if that's that easy. Yeah, it's just showing a harmonic quadrilateral. It doesn't seem like it should be that bad. It's the same as saying that so we want to show COK and this point are harmonic. Which wait, that doesn't even seem true. Now I am confused. Oh, actually, I think that is true. Yeah. We are so close. We just have a little bit more to go. Let's see. So okay, so it's the same as saying we want to show angle AGF is half of angle CAK. which is half of 180 minus CAI, which is 90 minus half of CAI. CAI, let me think about that again. We want to show that these are parallel, which is the same as saying this equals this, which is half of CAK. So we want to show FGA is half of CAK, and CAK is 180 minus CAI. So what's the angle bisector of CAI? Oh, so I think it's the same as showing AG is the angle bisector of CAI. And is that obvious? Feels like that should be an angle chase, right? Yeah, okay. I think maybe I'm just over confusing myself here, but oh, yeah, okay. I think it might be kind of obvious. So, oh, we wanted to show AN is perpendicular to GC, not. I think it's just an angle chase to show AN is parallel to GC, right? I think it is. Yeah. Okay. So, all right. We don't. Yeah. Let me delete some stuff that I don't really need. Okay. So first, I'm going to show AN is parallel to CG. That should just be an angle chase. Because angle NAC is half of angle KAC, which is half of 180 minus IAC. But angle IAG is GAC. So I'll write it like this. Let's do this. So angle IGA is GCA. So that implies that angle IAG is angle CAG. For IAG is GAC. Yeah, because we know this is a right angle and we know that this is a right angle. So then we have that angle NAC equals angle KAC over 2, which is 180 minus angle IAC over 2, which is 90 minus angle IAC over 2, which is equal to, that would be 90 minus GAC, which is GCA. Okay, so from there, see if this works. This drives me crazy, all this spacing. Now it just made it disappear. See if it works now. No. I don't know why it doesn't want to work. I think if I press enter, that might fix it. Yeah, okay. So let's think about this. So NAC is GCA, so AN is parallel to GC. And similarly, AN is parallel to BF. And okay, once we know that, then I think we can make a lot of progress here. So now basically an angle chase shows that AKO is similar to ATG. So so TGA is GCA. GCA, which is angle CAN, which is angle OAK, or angle CAO, angle OAK. So that's one of the angles. And we also have angle TAG equals angle GCH, which is angle AOH. So angle TAG is angle TAG is GCH, which is AOH. Or I'll say AOK. So those triangles are similar. TAG and KOA. And then similarly, we have FTAF is similar to KPA. All right. And then basically using ratios, we get that PK equals KO because we have KO over KA. So KO over KA is equal to AT over TG, which is AT over TF, which is PK over KA. And that means that KO equals PK. And then the angle bisector theorem solved it. So we kind of assume something here. So I'll just say T is the midpoint of FG. So AH. So AH is the radical axis of the two circles. It passes through the midpoint T of FG, since T has the same power with respect to both circles. Both circles, all right. So let's make room for that, so people don't get confused. So once we have this, then we can use the angle bisector theorem. So by the angle bisector theorem, actually we don't even, once we have this, we could basically use the angle bisector theorem to say that, because KO over KA is AN ON over NA. So ON over NA is PM over MA by the angle bisector theorem. And so that means that MN is parallel to BC, or MN is parallel to OP. And that means that the circles have the same radius. So same in radius. All right. So we have just a little bit of time left for one more problem. And I'm not going to be able to make it next week, unfortunately. So just letting you guys know now. But I can still probably do the week after, but I'll let everyone know. So I'll just skip making the tools for now. Let me look for one more problem from that Facebook group. So there were a couple good ones. Okay, here's one. I think we might have solved this one before, but I forgot the solution to it. So, and I couldn't figure it out. So you have a triangle ABC, and I might as well maximize. O is the circumcenter. It might be really easy, but I had to think about it for a little bit. AD is the diameter. And the tangent at D meets BC at a point. And then we connect that point to O, and meets AB and AC at 2 points. And basically, we want to show that O is the midpoint of FG. So I'm just going to use the same notation as the problem from the Facebook group. So this is P and this is Q. So yeah, it looks simple, and maybe it is, but I thought about it for a little bit, and I couldn't figure it out. So, all right, so that is the problem, and I'm just going to type up a description so that people watching know what the problem is. All right. And let triangle ABC have circumcenter O and AB as diameter. The tangent at B meets BC at E, and OE intersects AB and AC at P and Q. Prove that PO equals OQ. Okay. Antics of geometry. Facebook group. All right, let me just do some LaTeX. Screw the LaTeX. We'll just draw it like that. Okay. All right. Yeah, I think I've seen this before, but we need to prove that AP is parallel to Q. DP is parallel to AQ. Oh, it's a oh, that's a good point. It's a parallelogram. I don't know how I didn't think of that. Okay. So we want to show that's a parallelogram, which is the same as showing DO as a median. And I wonder if these triangles are okay. So triangles DPB and DQC are like, they're not similar, but they have one angle the same and the other angle is 180 minus. So it's kind of like they fit together. Like you could use the law of sine.
I think this is just Pascal's theorem.
Oh yeah. Okay.
Because if we draw the oh wait, no, never mind. But maybe that's still useful. So if we draw the points opposite B and C on the circumcircle.
Okay. I'll do it this way.
Then we want to prove that DQB prime and DPC prime are collinear.
And then it would actually be the butterfly theorem, right?
Yeah, I think so. Or just like we would have the parallels.
Okay. That would give the parallels. Okay, so basically, yeah, we want to show that these are collinear and these are collinear. Okay.
It might just be Pascal twice. I'm not sure. I'm gonna.
Okay. Let's see. So Pascal twice, or El Qadim. So yeah, then these triangles would be congruent. So QCO and OC prime P. So yeah, I'll delete these for now. So yeah, we want to show that these are collinear and these are collinear.
Yeah, if you use Pascal's on A, C, B, B prime, D, D, you just get that the intersection of D, B prime with AC lies on OE, and you're done.
Okay. So A, B, D, D, C, B prime.
I'm just gonna write it in the chat.
Okay, so yeah, O, E, and this intersection point are collinear. I see. So use Pascal's twice, and then that solves it. Whoops. And this. Then we have B, Q, and D are collinear. Yeah, so it's kind of like if we didn't draw this. So if we let Q, yeah, it's kind of like we're redefining. So let this be Q prime, and let this be P prime, and then we're showing that O, Q prime, and E are collinear, and then we're showing that O, P prime, and E are collinear, and so that proves it basically. So I'll rewrite it. Or let AB intersect C prime B at, so first of all, let B prime and C prime be the antipodes of B and C. Let P prime equal A, B, B, C prime, and define Q prime similarly. Then this would mean that O, Q prime, and E are collinear. And then similarly, O, P prime, and E are collinear. So implies P prime equals P and Q prime equals Q. And then once we know that, then it is the fact that it's the midpoint is just symmetry or the butterfly theorem. I'm trying to think.
It is butterfly theorem, but it's also just a parallelogram now.
Oh yeah, the parallelogram. Yeah. So then B, D prime, so A, B, D, B prime is a rectangle. So A, B, D, B prime is a rectangle. So then we have D, Q prime is parallel to A, P prime. Similarly, BP prime is parallel AQ prime, and that means that AP prime BQ prime is a parallelogram. And that means that PO equals OQ. Okay, so that one was pretty easy. And we have like 20 minutes left. Let's see. So yeah, there were some other problems. Oh, here's one that's really interesting. So I didn't know, I've never seen this before, but basically, if you start with any quadrilateral and you draw the Gauss line, then these two incircles are congruent. So this is interesting. So draw the Gauss line and see where it meets this side and this side, and then where it meets like A, B, and C, D. So yeah, you have to extend these two. And then so basically the problem is to show the incircle of AGI and CHJ are the same size. So let's see if I could draw this so it makes a better diagram. Maybe something like that. CHJ. So yeah, we want to show those have the same size. So let quadrilateral ABCD have Gauss line. What's a good? I'll say N. Let C1 be the circle tangent to AB, AD, and N. Let C2 be the circle tangent to CB, CD, and N. Prove that C1 and C2 are the same size. Okay. All right. So yeah, that was kind of how it was originally phrased on the website. So we could draw the centers. And we want to show they're the same distance. So it's the same as saying the line bisects KL. So then we'd have like three midpoints: the midpoint of BD, midpoint of AC, the midpoint of KL. I wonder if that's also the midpoint of GH. No. Yeah, I don't think it would help that much to use that area is in radius times semi-perimeter. I think maybe we could try something similar to what we did on the other pumps. So we know DK and DL. Well, see DK, yeah, those aren't angle bisectors. That's the problem. So it's not going to be as simple as it was before. We know that IK is an angle bisector, and so is DL. And also BL and DK. Oh no, DK is not an angle bisector. This is, GK is. And also, yeah, neither is DL. I'm just getting confused here. JL is. Wait, now I'm just really getting confused. BL, I did it all wrong. Okay, it's like this. There we go. We have to show IJ bisects KL. Yeah, this is really interesting. I think I've seen something somewhat similar to this, but it was a long time ago. And I don't know if it was this exact problem. I don't think it was. I wonder if we could like rephrase the problem. So like, what if we start with triangle IKG, and then we like reflect IG over one angle bisector and the other angle bisector to get A. Actually, yeah, I don't think my idea would be that good. Just thinking like, what if we hid BB? So basically, let's hide BB and AC for a second. We're basically saying we have these two triangles, and they would have the same incircles, and the line connecting their centers is bisected by. It's kind of interesting. Like, I wonder if we could work backwards somehow. Like, you start with like a line IJ, and then you take 2 points that are equidistant from that line and draw the circles, and then you could like complete well, but you don't know where G and H are. Kind of interesting. Yeah, it feels like this is like a really deep idea. So what's the theorem? I think for every point on the Gauss line, like the area of AFB plus the area of CFB is equal. I think that's the theorem. Like Leon, like Ann's theorem or something. So that would be true for the 2 points of tangency. So yeah, if I could zoom in and draw those 2 points of tangency, this point, then that doesn't look so great, but like if I take the area of MAB plus MCD, it's the same as what it would be for N. So maybe it's easier to think about it that way instead. Or sorry, yeah, MAB and MCD. So if it's tangent at M, I wonder, is this a parallelogram right here? I think it might be. Okay, that's interesting. No, I don't think it. Well, but I don't think I drew it right either, so. Let's check. Delete. So I want ML. Whoops. ML. And KN. Looks like there's a good chance it is. Yes. Okay. So I want to show that MLKN is a parallelogram. That looks like that's true. It looks like an important part of this problem. It keeps disappearing everything. So I want to show, well, we know Km and Ln are parallel because they're both perpendicular to the Gauss line, right? If I zoom in, it's just a tricky diagram. And the points keep disappearing, so I think that looks okay. So Km and Ln are both perpendicular to IG, so they're going to be parallel. But Kn and Lm, I'm not sure how you would prove that. Okay, it's 11:58. Interesting. All right, so I think I am going to stop here. This is an interesting, but it looks like a pretty hard problem. So thanks everyone for sticking around, and for everyone watching on YouTube, thanks for watching. So If you want to join us in the future, feel free to email me at mgreenby801@gmail.com. I won't be able to do it next week, but besides that, we meet at 8 a.m. US Central Time. So thanks again for watching and have a great day.